In this video, we will cover the Grasshopper definition for designing a small parametric lamp that can be 3D printed. The size of this luminaire is 120 by 150 millimeters, sufficient to hold an LED bulb inside. Let's begin. I'm going to hide this model and change to the shaded viewport. First step is to set the model dimensions by going to Tools, Options, setting it to millimeters. Then we open the Grasshopper window. Draw a point at the origin. We do that by creating a point at 0, 0, 0. We need to make multiple copies of this point in the Z direction. To do that, we need the move command. So we go to Transform, Euclidean, Move. Move command requires the geometry to move, which is over here, and it requires a motion vector, which can be created using a number series. We go to Math, Set, Sequence, Series. Over here, we can choose the number of copies that we want to make. So I'm going to set this to 150 and the step size of 1. We can multiply this number series with a standard Z vector, which will be under the Vector tab, Unit Z. We connect this over here and we connect these vectors into the motion input. What we get is 150 copies of this point, as we can see in this list. Now we need to create circles around these points. The way we'll create these circles are going to vary in radius, with the top and bottom having the minimum radius and the middle portion having the maximum radius. In order to do this, we will firstly create another number series, and this time we will use the range command. So we go to Set, Sequence, use the range. We need to create 150 numbers between 0 and 1. So the domain is set to 0 and 1. And the number of steps are going to be 149. So we take this input and subtract it by 1. So we take this 150 as A, use 1 over here, and these are the number of steps. And we get a list of numbers between 0 and 1. We take these numbers and multiply it with pi. Now we can take these numbers between 0 to pi and use it with the sine function under math. So you go to Math, Trigonometry, and use the sine function. And the resulting values, let me pull up a panel. The resulting values start from 0, it increases till 1, and the number 1 would be somewhere towards the middle, close to 1. And then it starts decreasing again all the way to 0. So it creates a harmonic numeric series. Now these values are important because this will be used multiple times during this definition. So we will take a number container and highlight it so that we remember. Okay. Now the first step was to create a series of circles. So we'll bring the circle command into the canvas. Here are the points that will be used as planes for creating the circles. And we need a set of values to create the radius, which is over here. Because these numbers are between 0 to 1, the radius is not sufficient enough in size. So let's multiply this with the number 20. When we do this, we see a series of circles which is the broadest towards the middle, but the top and bottom are really small. So let's ensure that the minimum size of the circle is 40 units, or the minimum radius is 40 units, and then the maximum can be more than that. So we can do that by using the addition and using the value 40 as the second number. Once we add this, now we get a set of circles with the minimum radius being 40 at the top and bottom, and then the maximum one being 40 plus 20, that's around 60. Okay, so that's step number 1. The next thing we are going to do is divide all these curves into 100 segments. So we have a list of 150 circles. Let's use divide curve component. That's the curve. And for count, we are going to change it to let's change it to 100. In fact, let's use a numeric slider. Yes. So this divide curve doesn't actually divide the curve, but it creates points at the locations where it's supposed to be divided. So we can use these parameters to shatter the circle into individual line segments spanning between these points. We can bring the shatter component. We're just typing it over here. That's the curve. And these are the parameters. Now, if you notice the parameters, we have 150 branches, and each branch has 100 different parameters. That means these 150 branches correspond to 150 circles, and each of these 100 parameters correspond to each of these points on the circle. So in order to match the data tree, we will craft the curve input. We get a list of 150 branches. That means 150 circles and 100 curve segments in each of those branches, which represents these individual curve segments. Let's hide this and let's simplify this. Now within these, let me just switch this on again. Within these, what we're trying to do is identify a shorter line segment, which is roughly 0.5 units in thickness. And then we offset, or rather extrude it to a certain distance. Now this distance can vary depending on the location of this segment. What I mean by that is, as this geometry bulges towards the center, the extrusion will also be maximum towards the center and minimum towards the top and bottom. Now let's see how to do that. Firstly, we need to identify a curve segment which is 0.5 units of this curve. In order to do that, we go to curve analysis and use the evaluate length. The length value will be 0.5, and we need to set the normalized parameter to false. So you right click on this, set this to false. So this is the point at 0.5 units, and its respective parameter is over here. We can use this parameter to shatter these segments again. So we go to curve, division, shatter. These are the curve segments, and these are the shatter. So we need to craft both the inputs and also simplify both these inputs. And simplify the output. The list that we get from this operation consists of 15,000 branches with 2 items in each branch. Now, if you look at the data tree or the way these paths are organized, you can see the first number represents the circle on which the circles that we created towards the beginning, and the second number represents these individual curve segments which resulted from the shattering of each circle. And the 2 values that you have over here represents the 0.5 unit segment and the remaining curve segment. The first item being the 0.5 unit segment, and the second one being the remaining part of the shattered segment. Now, to create an offset of this 0.5 unit segment, we need to firstly isolate this. We can use list item, and as I mentioned, the first output are these smaller segments. Now, once we have this curve, we need to find a number representing each circle that will define the extrusion or the offset of these line segments. To do that, we will again go back to the number series that we highlighted. So we have 150 numbers. And over here, we have some 15,000 branches. So firstly, we need to ensure that this data tree is organized in 150 branches. To do that, we will trim the tree. So we trim it, and we get a data tree with 150 branches and 100 elements in each. Now we can offset the curve, this being the curve input, and for the distance input, we will use these numbers. Take it over here, bring it all the way to the front, and because this value ranges from 0 to 1, we will use a multiplier to scale it up. So I'm going to multiply this with the number 5 and use it as distance. Since we have 150 branches over here, we need to craft the distance values. This gives us a variable offset of each of those segments, starting from 0 units as offset all the way to 5 units as offset, and then back to 0 again. And we have 15,000 branches with one item in each. This data tree represents the original segments, which are these, and the second list represents the offset segments. So what we really need to do at this point, and let me just zoom into one of them. Let's zoom in over here. Assuming these are the two curves that are offset, we need to create these lines. These two lines will be created by isolating the endpoints and then joining the endpoints. So firstly, we need to find the endpoints by using curve analysis endpoints. We find the endpoints of each of these curves, and we should also graph this over here. And we will copy it over here. Then we create a line segment between the start points, and then we create the line segments between the endpoints. There you have it. Once we have this list, we will now merge the two lines, the offset curve and the remainder part of this segment. We will do this for all 100 branches of each circle, and we'll do it for all the circles. This way we will get a combined joined curve that will sort of look like a gear, a mechanical gear. We bring in the merge component, and the order in which we merge is important. So we take the first line segment, then we take the offset curve segment, then we take the third line segment, and the remainder part, which is over here. This second item represents the remainder part of this segment. So we connect it over here. If you look at the result, the data tree doesn't really match, because what we should have is 15,000 branches with 4 elements in each. Now this issue happens because these datas have different hierarchies in their path. So it's advised to simplify all of them and also graph them. Now we have 15,000 branches with 4 items in each. If we trim this data tree, we get 150 branches with 400 items in each. We can use the join curve command to join all these curves into a single closed planar curve. So if we pull up a panel, we can see that you have 150 branches, each branch with a single closed planar curve. Let's hide everything else. Yeah. The last step that we need to do before lofting these 150 curves is to rotate them. Now for rotating these curves, we will again use the number series that we highlighted, and we will be multiplying this with the number pi. So we go to the number component, bring it all the way to the front, and bring in pi. You also bring in the rotate command. Here are the rotation geometries which are grafted at the moment. We can flatten them. And here's a list of numbers, a flattened list of numbers. We can use it as it is. And there we have it. Now to actually visualize this, what we need to do is loft these curves. And to visualize it properly, we can bake it. Switch to the Arctic viewport. And there we have it. But what we have at the moment is a single layer with no thickness. When you're trying to 3D print an object, you need to ensure that the geometry is closed. This geometry is a surface with no thickness. In order to give it a thickness, we will go back to the circles. Let's switch this to shaded viewport again. And I'll hide this at the moment. Delete this. So here are the circles. We can create an inset of this circle by using the offset curve command. So here's the curve, and the distance would be -1. We take these curves and we create a loft through them. Need to flatten these curves. Now when we cap, and if we cap these holes, we get two closed geometries. We can use solid difference command and subtract this geometry from this geometry. So that goes into B-reps A, and this goes into B-reps B. And the solid difference command takes a while to compute. We can hide the remaining geometries and bake this into Rhino. Hide this, and there you have it. And the way this geometry has been set up, or this definition has been set up, it's all parametric. So you can change any of these sliders and modify the shape as per the design intent. Although, before you do that, ensure that you lock all these components that take more than a second to compute. Otherwise, you won't see quick results.